hi, this is problem 214, and we are adding forces, right, in three-dimensional. So in this case, we have a pole right here that is sustained by two cables. We are given the values of the magnitude of this force developed in the cables. However, we want to find the resultant. To find the resultant, you know that the resultant force as a vector will be each of the forces as vectors. As you see here, these don't have any line up top because these are magnitudes. In order to find the vector, we have to multiply the magnitude by its direction. So let's start by finding the vector AB. So you know that a vector AB is the magnitude that we know times the unit vector that describes the direction. Any vector is described by two components, the magnitude and the direction. To find the direction, as you recall, is the vector divided by its magnitude. So to find the vector AB right here, there is two ways to find it. The vector AB can be found as position vector of B minus the position vector of A. That's why way to find it, you find the components of B, you find the components of A. The other way to find it is to do it graphically. So what we are doing is going from A to B, and we can go in a path following the coordinates, for example. So if we go down C, we go -3. So AB will be, I'm going to write it right here, -3 in K, and then I follow the y direction. I have to go 0.75 plus this here, this component right here. So it will be, for y, it will be 0.75. Let me do it a little bit bigger. I have the 3 in K, right? In J, and I have the component, let me write it here. The component in I, the component in J, and the component in K. So we were talking about J. I will go 0.75 plus this one right here. How much is this distance? We are not given this distance. We are given this diagonal distance, which is 2, and we are given this angle. We want to find this distance over here, which is the same as this distance over here. As you see, this is a right triangle, so we can say that this distance over here will be the diagonal times the sine of 40, right? So you see it for the top, this is a right triangle, and that will be the sine is always the opposite and cosine is the adjacent. So that will be, finally we can write that this is 0.75 plus 2 sine of 40. And in the x direction, so we already went down in C, y, and then we have to cover the x direction. And the x direction will be this one right here, right? And if we use exactly the same triangle, looking from the top, that this is a right triangle, we see this is the diagonal times the cosine of 40. So finally we have that this will be 2, which is the diagonal, cosine of 40. So this is my vector, and I have to find the magnitude. And the magnitude will be the square root of each of these components. And I have them right here. Let me write them down. So that will be equals to 3.9358. Remember, you could write less decimals. I could write a shorter number right here, but I have to use the whole number in order not to carry rounding errors for my rest of my calculations. So finally, when I multiply like this vector and divide it by the magnitude, I get that my unit vector will be this component divided by this. This component in J, right, divided by this, and in K will be this component divided by that. So let me write that vector over here, which I'm going to write it again, AB as a vector, divided by AB as a magnitude, and it's this component, which is give me 0.3389. 89 in I plus 0.517 in J minus 0.762 in K. This unit vector is the one that I will multiply by the magnitude, which is given, to find my vector AB. Let's do that. So my vector finally, FAB, will be equals to 250 times this vector, this unit vector, and that gives me equals to 97.3I plus 129 in J minus 191 in K. So be careful, as I said, with the decimals. If you don't save at least 4 or 5 decimals for each calculation, you will not get the same result. So we got the first force, which is this one right here. We have to do exactly the same for the second force. So let's do that with a different color. So now we are going to work in FAC. As a vector will be the magnitude, which again is given, times the unit vector AC. And this is a little bit easier one. Let's see. So let's find exactly the same process that we did. We will find the vector AC divided by the magnitude. And if you want to do it by vector position, you can also do it, and will be RC minus RA. Or you can do it graphically, as I did it for the first one. So AC as a vector will be, in C direction will be K, you see that, negative K. In Y will be, this is already at 75, but this point is at 1. So as you see, we have to cover this small distance. This small distance will be in Y, negative 1 minus 0.75. And in X, I cover only 2. So that will be 2 in I. Okay, so finally, 2 in I minus 0.25 in J minus 3 in K. I have to find the magnitude of that vector, which will be square root of 2 squared plus 0.25 squared plus 3 squared. And that gives me a value of 3.614. Now that I have the magnitude and I have the vector, I can find the unit vector. So the unit vector will be equals to that vector that I found divided each component by its magnitude. Let me write it right here. So it's 0.553 in I plus 0.0692 in J minus 0.8. I'm using 3 decimals in each. Let me use 3 decimals. You just save the decimals in your calculator, please. In K. So now that we have the unit vector, we did exactly the same as here. We can find, finally, the vector AC. So that vector will be multiply the magnitude, which is given, which is 400, times this vector over here. So it will be 400 times this value will give me the I component. 400 times this value will give me the J component. 400 times this value will give me the a K component or a C component. Let me write them down. 221 in I, negative 200. Oh, this is negative. Sorry, this is a negative value. Negative 27.7 in J, and negative 332 in K. And I like to remember that, don't forget the units. I forgot the units right here. Let me write that down. This is in newtons. Very important to keep track of the units. And here as well. And then we have this value right here. So we were able to find this component. Now we are able to find the resultant force, which of course you know that it will be equals to the component in I plus the component in I, the component in J plus the component in J, and the component in K plus the component. So let me write it down right here. As a vector will be 97.3 plus 221, and that gives me 318.67 in I. I will add this value plus this value, and that gives me 101.63 in J, and then I will add this value and this value, both negative, so it gives me a negative value of 5 to 2.5 in K. All that newtons. So I was able to find the resultant force in terms as a vector with three components, because we are working in three-dimensional space, right? Now, they want us to find as well, not only in vector form, but in magnitude and direction. So let's do that. Over here that I have a little bit of space, the magnitude of a vector will be the square root of each component. So that would be 1867 square plus 101.67 square plus 522.5 square. And that gives me a total of 620 for 46 newtons. So that is the magnitude of that vector, and this is a vector and this is a scalar. So because that's now the magnitude, look at this, I have to erase this line over here because the vector is the notation of a vector. I'm using a little line in top of the name of the vector, and here is a scalar, so I don't have a line over here. And to find the direction, so where would that vector go? You see that this is positive, so we'll have a positive component in X, a positive component in Y, and a negative component in C. So it will be somewhere around here. Now they want us to find the angles that this resultant force form with the axis. So I have to find alpha, as you recall, is the inverse cosine function of the x component divided by the magnitude of the vector. That will be cosine of the -1 of the x component is 380.67 positive, right? Divided by 620, where is 6? That gives me alpha is equals to, I have the values right here, 59.1. Then beta, which is the angle that it forms with the y-axis, will be this angle right here. This will be beta. This will be alpha. And the one with the z-axis will be gamma. It gets a little bit crowded, the drawing, so that will be cosine of, this is a negative, this is a positive value as well. And beta gives me a value of 80.6, and gamma, which is the angle between the resultant force and the z-axis, therefore I use the z component, which is, the z component is a negative component, right? Divided by the magnitude. And that gives me finally gamma, which is 147.38. As you see again, anytime that I have a negative component, I get an angle that is greater than 90. So those are little things that you should use to prove that your results are correct, right? So whenever you get a positive component, you have to have an angle less than 90. And for a negative component, you have to have an angle positive, because this angle here is greater than 90. It is always very important to check the values that you are getting to see if they make sense. So if we have two forces, right, those cables are pulling that pole, the resultant force has to lie in the middle of those two forces, because it's a result. I am adding those two vectors, and I have to get something that is in between those two vectors.